So, hi everyone. As I said, we only have Thomas today. He's doing his PhD in Lisbon, and he will talk about developing speech therapy games for children with speech disorders. And I think you can start, Thomas.
Okay, so hello everyone. So as Julie say, I'm going to talk about developing speech therapy games for children with speech disorders, and this work has been done under the supervision of Professor Alberto Abad. And yeah, let's start. Okay, so first as introduction, as you probably know, some children may have some communication disorders that can lead to problem in feeding and swallowing, articulation, fluency, voice, and all of that is critical for children as communication, and especially when you're a child, like it's very important in your development that will lead to what kind of adult you will be later. So communication and be able to communicate through language and speech, it's very important. And that's why usually when some children have this kind of problem, we usually, to help them, we send them to speech and language therapy. It's usually done in a hospital or a clinic, and as it's usually not enough because you don't have as many time as you would like to have with the therapist. You usually have some exercise that you have to do at home. And this setting, there is some like drawback of this setting. So first, you need an expert therapist to assess the children to be sure that the exercise is well done, that the children are making progress. There is also the problem that children have a very limited attention span. So if you ask them to do a very repetitive task again and over and again and again, it's going to be very bored easily, and they're not going to be focused on the exercise. So it's quite important to take into account. And also some hospital and clinics can be a stressful environment when you're a kid. And this is where speech and language technology tools, so SLT, tries to help. So for instance, where instead of having the need of an expert all the time, we can have specialized algorithm artificial intelligence that at least can recognize better mistakes and help better the children than can do the parents sometimes. For the take of the problem of the limited attention, we usually present the exercise in a gamification framework, so with rewards. So we keep the kid like interest and like wanted to do more exercise in a way, and want to go back to the exercise also, because more exercise it does, better it is. And some of these tools are also possible to do them at home with their own computer or on a tablet. So it's way less stressful environment than doing it in hospital and clinic. So here in Escadi in Lisbon, we have like a bit of experience with that kind of tools since we are doing them like for quite a while now. And here I just plot some of the examples. That's the one we developed in the past. And if we focus mostly on the speech SLT tools, it's gonna look like this. So this is like a rough summary how it works. Of course, it can be different for each, but it's just to understand mostly. So you have the exercise creation, which mostly can be like reading task or any task that you can do with the therapist. It's presented to the children in the form of a game. Then the children is gonna speak. They're gonna have like this speech recognition component. And as, for instance, when it's reading a prompt, we have a priori knowledge. So we have already the expected transcription of what the children should say. And then, of course, we have the result of the speech recognition that go into a mistake recognition. And then here we can give statistics back to the therapist and even update the exercise. And of course, the therapist by himself can update the exercise if a children have some difficulty with a particular exercise, and you tend to do more this exercise. Something which is also interesting this kind of tool, and that's I think I've been working on, is instead of just giving back statistic like audio rate or like the number of repetition and this kind of thing, we can think about giving information such as pathology and disease information. So that's thing I've been working also on. I'm not gonna dive into detail in this talk today because I don't have enough time, unfortunately. But you have the paper here. So mostly we can detect pathology speech using X vector. It's about this one was about Parkinson and obstructive sleep apnea. We have some work I've been working on here also on Alzheimer's disease, and here it was not on speech, but it was on cough, and it was to detect COVID. And the last two paper has been accepted to enter speech. So today, as I mentioned, I'm not going to focus on that. I'm mostly going to focus on the automatic speech recognition model, because to have this whole system working well, you need this Oracle model, which is working well, because you want to detect mistakes. So if your model is making mistakes, is not good. You need a model that work well for children. And to have a model that work well for children, there is some challenge. So let's dive into children automatic speech recognition. So there is a drop of performances when compared to adults. Nowadays, with deep learning, when you train a system on adults, it can give very good results. We can see it with LibreSpeech dataset, for instance, with the end-to-end model nowadays is giving like super good whatever rate results. But if you use the same model on children's speech, they will have like a huge drop of performances. And it's the same even if you train this model from scratch using only the children's speech, then they also is not going to be as good as adult. And there is three main reasons behind that. And the first one is the eye, enter, and intra-speaker acoustic variabilities. And this is explained by the fact that this is a speech production system from a children, and this is a speech production system for an adult. And as you can see, there is like a lot of differences. And as the children is growing, like it goes from here to here, usually reach that point around 14 years old. And of course, it reflects in the acoustics. Usually it's a pitch informant shift. And of course, so if you take two different children, and even if you take the same children at different age, like the acoustics will be different. And that's very hard to model for an RSR model. Then we also have the limited linguistic knowledge. You can't really expect for 6 years old or 7 years old children to use as complex sentences and complex vocabulary as an adult. So usually when you train a model on adults, the language model is trained on adults on sentences, construction, and vocabulary of adults and not of children. And the last challenge of children automatic speech recognition is that, as I say, like nowadays we use deep learning. So we need a lot of data to understand variabilities and like to be robust. And for children, we don't have a lot of data, and it's not most of the time is less than 50 hours. So to learn these different variabilities, the linguistic and the acoustic variability, we need a lot of data, and we don't have it. So that's also the third problem of speech recognition. And so now I'm going to present two different approaches that we tried to tackle this problem. So the first one's going to be on HMM DNN based, and the second one's going to be on end-to-end. But the first one is multilingual transfer learning. So it's a work that has been accepted for RREC this year, so 1 month, 2 months now from now. And mostly this work is based on two other methods that I'm gonna first mention now. So the first one, I suppose everybody knows about that, or it's very well known in the community right now. It's transfer learning. So mostly, but I'm just gonna quickly recap what is it. So mostly you have a target and a source task. The source task is well defined. The target task is like a low resource, for instance. In our case, it's a kid. It's a children's speech recognition. And you initialize the weight of your target task by using the weight of a pre-train on source task, pre-train models on a source task. So usually what people do on children automatic speech recognition is that they first train an adult model. They train this adult model. So the adult model is gonna learn pattern all the adults are speaking. And then we take the weight of this adult model and we just fine tune the weight with the children data. There's this second step is gonna like fine tune the weight in order to fit better with the children using the knowledge of the first one. And here for the rest of this presentation, the white is going to be randomly initialized and the gray is going to be already pre-trained initialized. And we did this have been, of course, successfully applied to children automatic speech recognition, but we also validated it by our own experiments. So we validated it on HMM DNN, but also on end-to-end. The second method that people can use to tackle this children automatic speech recognition problem is multitask learning. So it's a bit different from transfer learning, where transfer learning you have two steps. Here you have only one step where you train all tasks. So you don't necessarily have two tasks, the source and the target. You can have as many tasks as you want, and you train all these tasks in parallel. And how you do that is by dividing your network into two parts. So the first part is the shared layers. That's what we have here. And then we have the task-specific layers. So mostly here, each task is a language. And if you have like a data from language 1, it's going to go through the share layer, and then it's going to be routing to the language-specific ones, and with the number of output corresponding to this one. And if you have the language n, for instance, it's going to go through the same share layer, but then it's not going to go here, it's going to go to its corresponding branch. And by doing that, you learn shared representation here. And in case of children automatic speech recognition, when you do that with different language, for instance, this shared layer should represent all children are speaking, and the language specific will be all children from, let's say, English or Mandarin here are speaking. And these have been applied to English and Mandarin successfully by these two work here. And this is where we came up. We decided to say, okay, we have these two different nice methods, and we wanted to combine them. So this is what we did. So we had the multitask training. This is exactly the same as I first explained just before. But instead of that, since we have no like shared representation and of all children are speaking, and we have all of this knowledge, it could be nice to only fine-tune it over one single target language. Because as during this multitask, they're all fighting to each other to like get the best results. This is the multitask training. And just by fine-tuning over a target language will be like better to maybe get better score. So what we have here is we first train our multitask, and then we fine-tune over target. So this is why it's gray here, because this is pre-trained weight from this step. And if the target language was present in the first step, so if let's say it was language 1, then we already have pre-trained weight also for the language specific branch, so here. But one interesting thing about this work is even if the target language is not present in the first step, we can still use this shared layer and just like randomly initialize the language specific. And by doing that, we still use the shared layers of the characteristics of children that have been learned in the first step. So in order to validate, we use 5 different datasets. So that's the dataset we use for experiments, and I sort them by hours. So smallest on the top and biggest on the bottom, and all of them are different languages. And as you can see, we have 4, like around 5, 6, 12, and 20. So it's way less from what you can find for healthy speaking adults, when you can find at least 100. Here, like, yeah, we really use like very small one. And in terms of input feature, we use a 40-dimensional feature bank, and we use a 40-dimensional spectral subabundance rate. So spectral subabundance rate is just you divide, just use your spectrogram into 40 dimension. For 40 subbands, and for each subband you compute the mean energy of each subband, and then that's your feature. And we show experimentally then that this spectral subabundance rate feature, when you concatenate them to the filter bank, it slightly improves children automatic speech recognition by giving more explicit information on the performance, for instance. And we also use a 100-dimension speaker embedding here, I vectors. We also use data augmentation. This is something that is usually done when you train this kind of model with volume and speaking rate perturbation and spec augment. And in terms of model, for all of our experiments, we use always the same model. So it's for the share part is 6 CNN and followed by 7 factors time neural network. And for the language specific part, so the branch, each branch for each language individually, we have 2 TNN, 2 TGNN, and 1 full connected. And all of this model have been trained using lattice frame MI and cross-entropy regularization. So let's look at the results. Here, so we have the result in order of rate. So the lowest, the better. And I still sort on the left is like the smallest amount of time we have to train, so 4 hours, and on the right it's our bigger data set. And I just show here's the language. So if we train these models that I just described, this one with all this input feature, with this data augmentation and this lattice frame cross entropy, just on a single language, then we have these scores. And as expected, more you go on the left, higher is the order rate, because you have less data to train. And more you go on the right, lowest this will be. We just have this CMU outliner here, which is here because CMU task is like very limited, is prompt text that you don't have to read, and it's very limited vocabulary. So it's make the the LSA model work like a bit more easier. So that's why we have such good score here compared to the others. So then we wanted to assess how the multitask is working, because in previous work, they use only 2 languages, and it was quite well, big data set. There was 100 of hours, but in our case, we have like the biggest one is like 20 hours. And we have 5 languages. So it's a bit more complex. And indeed, it is more complex because most of the case, we don't outperform the single language. Even sometimes we degrade it, for instance. So it's a bit in contradiction with what I've been in some paper before, but it can be explained by the fact that, yeah, we have 5 and it's smaller, so they are competing more each other. So it's a bit more complex for the language specific to really like understand well how to work. Then we wanted to assess the transfer learning. So taking, for instance, each single language and then fine-tuning it over all others. So for instance, here for this line, we take this PF star, so this model, and we fine-tune it with the TLT here, with the CMU here, the let's rate here, and the Shrek here. And same for all of the data sets. So for each one, we fine-tune over all others. And something we can see is that the average and also the best is always better than the MTL and the single language, which confirm that transfer learning is a very, very good way to help children's speech recognition, to improve the scores. And something interesting that we can also see here is that the Shrek, so our biggest data set, when you transfer learning over this model, so from the Shrek, this is where you get the best result. And this is mostly this confirmed that more data you use in the source and in the source task, better it is. So because it has so like more variability, so it's better. So now that we have the MTL, the multitask, and the transfer learning, let's see our method performs. So we take this line, the multitask learning, and we fine tune for each column individually. And so we have the gray here, so pre-train, because all tasks have been present in the multitask. And what we can see is that doing that, we outperform slightly the best transfer learning, and we are beating all the scores anyway. So doing that is better. So it means that during the multitask, they were like still learning things in the chart, but since they were competing to each other, it wasn't as good as for instance, transfer learning. And doing this transfer learning second step help really the model to use efficiently the things that have been learned in the multilingual phase. We also wanted to assess a bit more. So we did this experiment of 1 language out, where we train a multitask over all languages. So for instance, we take this language here, we want to assess this language. So we do a multitask over all others. And then we do the second step, the transfer learning over this one only. And here's the same. So we take this one out, we train the multitask over all others, and then we just fine tune it over this one. This is why it's white here, because it hasn't been present. The column hasn't been present in the first step. And doing that, we are better than the transfer learning in most of the camp, just slightly, or like very, very close. So it's as good at least as the best transfer learning. And that show that, yeah, like this shared layer learns something about children that can be used efficiently during the transfer learning phase. So yeah, that was the first work we did. So I'm gonna dive in the second work. So mostly what happened in that time was like the community moved to end-to-end. So we decided to propose what we call adapter and variational adapters for end-to-end speech recognition of children. And this work is still under review and have been submitted to Anticipate this year. So mostly, as I say, nowadays end-to-end, especially transformer-based, yield best result for children ISR. So this is here an example of a transformer architecture. But for us, it was like a bit tricky because we want, as I mentioned, for application, for the game, for the children, we want something which we need like age dependent. That would be nice. Even speaker dependent would be even better model. But then it means that we have to store everything again. So a transformer model is a lot of it's very big, so it's not easy to store. Especially if you fine tune everything, and training is also like very hard because yeah, it takes a lot of time, and we have the problem when we do transfer learning of catastrophic forgetting. So when you fine tune all the weights, then you don't have any way to recover what was the initial model, and that was a bit of a problem. So what people propose is to use adapters, so that have been used in NLP first. So mostly you have your transformer layers that are your plot in the red boxes, and you add. So this is here just a zoom in, and you add this like this adapter box kind of. And when you train it, you just froze everything else except your adapter. So you only train the adapters, or everything else is like froze during training. And this adapter, mostly what is it? It's just a norm, fully connected down and fully connected up. So it works as a bottleneck. And it was good, but we were thinking, okay, shouldn't there have this a lot of variability? So what if we add, in addition to the fully connected down, we add like this. So this is what the fully connected down, and we add like some variability here. So we kind of get inspiration from variational autoencoders. And the idea is like, instead of doing directly like fully connected up and decode the bottleneck, we just consider this as the mean, and then we have this as the variance, and we just sample over this with the condition by the mean and the variance with sample, and then we reconstruct. And by doing that, we hope that this term here is gonna understand where are the variabilities in children's speech. Okay, so I'm a bit over time, so I'm gonna just keep the loss function, but mostly we just, when we do variational, we just have a Kyle divergence term. Yeah, so data set. So we use the biggest data set, which is available right now for children, which is a My Science tutor. It's English, and it's around 100 hours. So it's way bigger than the previous experiment. And in terms of experimental settings, so we pre-train the model on LibreSpeech. We use the 80-dimensional theta bank. The encoder is 12 layers of transformer, decoder 6. We use attention SCTC loss, and for all adapters, we use a fixed dimension, ident dimension, so at the bottleneck size of 384 with early activation. And then here I just show the hyperparameters value. Okay, let's type to the results. So if we don't fine tune anything, we just test on the test set of My Science tutor of the children using the adult model. We can see we have this 31%, which is quite good compared to what we could have expected. But this is because the My Science tutor is like a bit older children. That's why we have such low whatever rate compared to what we can expect. If we fine tune everything, we get like a huge improvement, and we can see here that we train this amount of parameters. So if we want to store this model, we have to store this number of parameters. Then we decide to go with the normal adapters. So adapters on the encoder and decoders. So for each transformer layer in the encoder, each transformer layer and the decoder, we only train this. All the rest is fine-tuned. So the train parameters is like, as you can see, slightly like a lot reduced. And the whatever rate score is very close. It's slightly worse, but that's expected from adapters because we don't train as much as the fully fine-tuned. And then we wanted to see if it was more important to use adapters in the encoder or in the decoder, and it is more important to use in the encoder. So there is more acoustic mismatch than there is linguistic mismatch. And that's also something which is known in the literature. And we just wanted to assess also a bit more about this size here. So we play a bit with this size, and we saw that more you increase the size, more you add parameters. And so if we add parameters, like we're getting closer to the fine tuning. So this is here is a relative whatever rate delta compared to the fine tuning. But yeah, around like 15% of the number of parameters that you can train here, you can get like pretty similar scores and then fine tuning. And then our variational. So as you can see, so we try here to use it on variational in encoder and decoder layers, and it gives like better result, at least at the simple adapters. Then we try to use the variational because it's supposed to work better on the acoustic. So we try it on the encoder only and keeping the normal adapter for the decoder. And this is what gives us like the best result, and we're getting way closer to the fine tune. And then we also, like as previous experiment, we assess if it was better to use it on encoder and decoder only. And here I put like these stars here because of course there is more. So you can say, okay, it's not really comparable, but then when it's only when you train, when you store them and when you do inference over them, you get rid of this sampling and of this variability because you don't really care anymore because it's the mean should be captured here. So mostly what it says is that these two are like at the end are the same as this one, and this one is the same as this one, and this one is the same as this one. So this is comparable. This is just to explain why it's comparable. And so yeah, so these adapters are giving quite good results. It's way smaller to store and to train, and so it's a good alternative to fine-tune the entire model for like for tablets and like cloud devices, for instance. And in terms of current work, so we want to investigate on new adapter architecture. So we want to use X vectors, big embedding also, maybe to do better adaptation. We also want to do attention fusion. So the idea will be to train different from different age adapter for different age, and then like using attention to fuse them. But for that, we need new data because my sense tutor is like the age range is kind of small. And we also want to investigate a bit more about transformer layers. And we saw, like we did already preliminary experiment, and we saw that if we fine-tune only the feed forward is like already giving like the best like score adaptation score. So this is the most important thing to fine-tune when you fine-tune over transformer layers. And we also want to use TTS as data augmentation, as we maybe want at some point to do like speaker dependent system. And I don't know if I have time, but I can play some of the preliminary like result of the TTS systems that we have. What do you think, Julie? Do you think we have time for that?
You can.
Okay. So mostly what this model, this is a single model. So it's not one model trained for each children. So this is always one single model. And we have the original here. You don't hear the sound, isn't it? Maybe I can share again. Let me just share again with the sound. Yeah, share audio. Okay. 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 Yep.
I noticed that the sand and...
Can you hear the sound? Was it?
Yes.
Okay, so that's the original children, and then we try to copy his voice with one single TTS, one single model of TTS.
It took me quite a long time to develop a voice, and now that I have it,
So of course there is artifact and everything, but it understand it was a girl, and it kind of captures some of the children characteristic. Then we have this one.
The gas and coal are different because coal is mostly not used.
And the TTS for this one.
It took me quite a long time to develop a...
So that's the exact same model between the two. It's just we give like different speaker embedding in a way to the model. And it captures like a bit more like it captures the children characteristic. And
the variables we did was first we changed the cup size.
And this one is interesting because it's a little girl, but the rhythm is very slow, and the TTS model is understanding that her rhythm is very slow.
It took me quite a long time to develop a voice, and now that I have it, I am not going to be silent.
So yeah, so we have this model. Unfortunately, so far it doesn't work because, like as you can hear, there is like a bit of artifact, and it's not as good as we want. But that's also something we want to do in the future, is like be a bit, yeah, do data selection technique and fine tune a bit more the models with that. And yeah, that's all. Thank you. And I have here the reference of the different corpus. Yeah. Sorry, I'm a bit over time.
No, it's okay. Thank you, Thomas. Do you have any questions for Thomas?
I have a question. Hi, Thomas. Thanks for your presentation. You've used this different corpora in your two studies, but do you have an idea of how end-to-end compares to transfer learning in terms of performance?
For the small data sets, you mean?
Yeah, no, for children's speech recognition in general. For us, well, the data sets are often small for children's speech recognition. Yeah.
Well,
end-to-end better or transfer learning?
Yeah, like there is like at least 2 studies that investigate on transfer learning, at least end-to-end, and one is like the one I mentioned before. Where is it? Yeah, this one, and there is a second one by Lucille, which is also here today in the Zoom. And for this one, they use the exact same data sets, so they use the MyScience tutor, but I know that Lucille used a French in-house data set, which is smaller. So it does help. Like transfer learning, even end-to-end, is way better than fine tune it, like do at least train from scratch. That's for sure.
Excuse me, which one is better now?
End to end, or like you first train an adult model and then you fine tune it
Yeah.
on transformers.
Okay, thanks.
Oops.
There is also Bence. He can't talk, but he has a question on the chat. He's asking if why do you think shared representations help ASR performance? That result seems to be inconsistent with Feng's paper, who show that multiple languages actually hurt ASR performance, although they evaluate on the phoneme level. Do you know what might be the reason behind the different conclusion?
I'm just going to check if the Feng paper is the one I mentioned. It should be here. No, okay, it's not. I didn't know what is this Feng paper. Okay, but mostly what happened in our experiment is that, yeah, like the multitask. So when we have this shared representation, we have such small data set and kind of imbalance because we have like 20, if you look at the data set, we have 20 hours of Dutch, but only like 4 hours of Swedish and 4 hours of Italian speaking by German. So that they are competing. This is the all multitask is working. They are competing to each other. So each one is trying to get the best. And when you backpropagate, they try to get the best out of it. So of course, the fact that it's in balance and the fact that we have small data sets, this is why we have like worse results than the previous work. Like in previous work, when they use Mandarin and English, they have like 100 of hours while we use 20, and they only use 2. So it's way easier to train this representation, shared representation, when we have like a lot of data and more balance in a way. That's why we have such scores.
Sebastião, do you have a question?
Yes, it's not much, it's just a curiosity. First of all, thanks for your presentation, Thomas. Do you know if you pass the results from the text-to-speech data augmentation that you did through like a speech enhancement pipeline or something like it, if you could get rid of the artifacts? I don't know if it's something that is feasible or not, or if it's done nowadays. But the quality seemed pretty interesting, and maybe if it's just the artifacts, I don't know if it could work or not. It's just more of a perspective.
Yeah, there is different strategy with the TTS right now. So far we use like one data selection technique, which is mostly, well, I can maybe just go back to the slide. Yeah, so mostly we have the original and we have the TTS, and what we do when we give we capture the children characteristic of the original is by using the speaker embedding. So we extract the X vector and then we give it to the system that generates speech using this speaker embedding. This is why you capture information such as all children are speaking. And at the output, it gives us directly the wave. That's our model. So our data selection so far is like we take the X vectors that we have from the original and we compute this with the same X vector extractor. We compute the X vector of the TTS, and we do like a cosine similarity between the two, just to be sure that they are close. And we have a threshold around 0.8. So if they are under 0.8, we just get rid of the example we consider is noisy. But doing this is not enough. In previous work, it's enough because the number of children they use, like they fine-tune one model of TTS per children. But for us, we want a model that works for any children. With only one model, so it's way more tricky. So there is, yeah, maybe like this speech enhancement would be a solution. We'll also, there is a work from ICASP this year that's also proposed to use normalization, 2 different normalization, one for the normal children when you do fine tuning and one for the TTS. So when you do the normalization, then it's like it captures the children speech artifact from the TTS and not the children speech in general. So there is, yeah, like things to do, but with the TTS, but yeah, that's current work. But like definitely the speaker enhancement, like the speech enhancement would be also something to try.
Okay, thanks. It's super interesting. I find, and since you have the pairs, I don't know, maybe it could work, maybe it couldn't, but well, thank you.
Are there other questions for Thomas? As I said in the beginning, Bence can't present his work today, so if he's okay, I think we will reschedule him later. And you will find this presentation soon on YouTube. You are okay, Thomas?
Yes,
He
yes.
signed the agreement, so
Yeah, I signed the agreement. It's too late anyway.
it's too late. And thank you for your presentation. And we'll have a next one next Tuesday with Thou and Eno. So thank you everyone for being here, and see you next week.
Bye.
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 All right.